this computer. And we are recording. Okay, so today I want to talk about more evidence that light is a wave and some of the physical effects that this has on the world we see around us. And some of these things aren't obvious. And in fact, people didn't notice this stuff for hundreds and hundreds of years. The question of whether light was a wave or a particle has been around for hundreds of years, but it wasn't until really in the 19th century that people started paying attention to this stuff. And so we're going to talk about some of these classic bits of evidence, and I'm going to sort of be a little bit fuzzy with some of it, and I'll really concentrate on two-slit, but I'm talking about other stuff. So one thing that we know about waves, right? So if we just think about water waves, one thing that water waves do is that they bend. So if I imagine I've got some waves coming in from the ocean coming this way, right? So here's the crests of some waves that are traveling in from the ocean. They're all traveling to the right. Let's get this. And then let's put like a dock or something, or some bits of wood, or some land masses or something in here. And as the waves hit it, one thing we know is going to happen is the waves are going to spread out from there. Let me show you a picture of that. Let's share. So I've in chat, let me see, where's my chat window? Let's see. Can't find my chat window. Hold on. Where did I put it? Come on. Did I post something in chat or didn't I? Oh, there it is. Okay, there's the chat window. So if you want to go to this website yourself to play with it, I'm going to be playing with this all class. So if you want to bring it up just to play with it while I'm talking about it, that can be fun. Or you can look at it afterwards. So here is a little computer demo of waves coming in from the left and hitting a jetty. And these are water waves. And we could do this in real life by having a tank of water with the stuff moving up and down. We actually have a demo that does this in the department. But this is kind of what you're going to see. So if I put this thing, right, so I'll just move this out so you can see it a little better. So we have some waves coming in, and then they hit this hole, they spread out around the hole, right? So they don't just go straight. Now, if you change the wavelength of the waves, you shorten the wavelength of the waves, it behaves a little bit differently. Let me make that a pretty big hole in there. And now what you can see is they're still spreading out, but instead of spreading out all around like a circle, now it's spreading out sort of just curved on the corners. So if I stop share screen, visualizer, right? So if I have my slit if my hole is very narrow compared to the wavelength of the stuff coming through, it kind of spreads out circularly. And if the hole is really big compared to the wavelength, then what I get is I kind of get sort of this sort of thing happening. It's still, I have this central part where the waves are sort of coming through evenly. It's only on the corners where it's kind of spreading out. Now, the big difference between these two behaviors is what's the wavelength of the waves compared to the wavelength of the opening. Now, you might say, well, this doesn't happen with light, right? Well, in fact, it does. And there's several reasons why we don't notice all the time. Let me show you one picture, which is pretty cool. This is a real picture. I keep moving to the wrong share. So new share, visualizer. This is actually a picture of a razor blade. There's the holes in the middle of the razor blade. And here's the sharp edges of the razor blade under monochromatic light. This is light of just one color. And if you do this, you actually see, wait a minute, you get this weird stuff around the edges, these fringes. This is actually light bending around the edge of the razor blade. You can do this yourself. There's lots of different ways you can do this, but one way you can do it is you can use a pinhole. So let me show you what happens just in the wave simulator. And I'm not going to tell you why this happens or go through the math of why this happens, but we can talk about it a little bit. So what I'm going to do here is I'm going to change it from either working with water waves to working with light. And I'll make it a pretty big slit. That's fine. So, so here what I have is here I have light coming and hitting a hole, and in the hole, the waves go straight through the hole horizontally, but then they curve at the edges. And what you see is you see a big fat distribution of the light. So the thing on the right is showing me how much light I have. So the thing in the middle, if I turn this thing off, that thing on the right is telling me sort of what I would see. I'd see a big wide spot. And if I graph how much light I'm seeing at every place, it would look like that. Now, one thing I can do as I make that slit smaller, let me see, where can I find it here? Let me try some bluish light or some greenish light. Now this one will diffract less, so the spot will be narrower, but we'll also see something else cool here. Let me turn it up a little bit more. Let's make the slit a little smaller. So now we can see, what's going to happen for me here? It's finding its equilibrium here. I need to do it one more time here. There's some little wings that you'll start seeing. Actually, that's split width's too narrow. Let's try that. Now you can see, now you notice at the top and the bottom of the intensity plot, you're seeing these little bumps coming back. And that's a particular characteristic of waves, is you see these secondary interference effects. And we could talk about why, and the textbook goes through it a little bit, but we don't really have time to get into the math of how that happens. But it does happen. Now you can check this yourself if you just want to get a small piece of tinfoil. You get yourself a piece of tinfoil, and you take one of the pins we gave you, and you poke a tiny, tiny little hole into the tinfoil. Let me see. Stop share, start share, share screen. I'm flipping back and forth between things too much here. So I've got a tiny little hole. Probably can't see that there, stuck in the tinfoil. And then you can take your laser. Now the laser is, the important thing about the laser is that the laser gives off only one wavelength of light. Most light that we see from a light bulb or from the sun is a very broad spectrum. You're seeing many, many different colors of light. Lasers are nice because they give off only one wavelength. They've got other features as well, but the really important one for us is there's only one wavelength. And if you shine your laser, let's see, if you take, yeah, I want the red one. So I have my red laser, and I'll shine it on that hole. Now I'm going to get lots of reflection back into the camera, so I'll move it back in the camera. Let's see if I can find it. Gotta get it on the hole. All right, and you can see the light. Now what I'm gonna do is I'm gonna stand up and do it from far away so the light has lots of room to spread out. Where are you? And this is something that's fun to try on your own. Oh, I have it there. Come back. And one thing you'll notice is that the spot is much, much bigger than it was at the pinhole. And the second thing you'll notice is that you're seeing this stuff outside the main spot. And if you do this and you throw it across the wall, which I can't really show it for you, what you see, and here's a really good picture of a really good pinhole, is you see something like this. Share screen, share my thingy. You see something like this, is you'll see circular fringes around the main hole. And those are the equivalent of those little bumps that we saw in the thing. There's many, many little bumps. And so this is the light not just going straight through the hole, but spreading out after it gets through the hole. And you'll see this more with red light than green light or blue light, because red light has got a longer wavelength. So the hole looks very small to that light, and so it spreads out quite a lot. And so this is what you're seeing. You're seeing the spreading out, and you also see this distinctive pattern called the diffraction pattern. Now, we're not going to talk about that precisely, but what I do want to talk about is something else that happens, which is two-slit interference. And two-slit interference is actually easier to understand than just a single slit. So let's talk about how that works. Stop share, start share, visualizer. Okay, so what I'm going to have is a situation. So the first thing we remember about waves, right, is that they add. Is we have something called the superposition principle, which means that if I have a wave that looks like this, traveling down a string, and at the same time, like maybe going in the other direction, I have a shape that looks like this, and it's on the same string, when they hit, I'll see something, you know, like the two added together. And when they add up, when I have something that's high and something that's high, that's called constructive interference. And if I have something that's going downward, something downward, and something that's upward, so this guy's headed this way and this guy's headed this way, so we wiggle the string from two different sides, then we could get something that's even flat, and this is destructive interference. And this can happen in more than one dimension. This can happen in two dimensions. We started talking about this a little bit in class, so I'm going to go back to some of those questions we talked. You may remember this guy. Source A, source B. Okay, we're on having trouble with your camera, but yeah, this is going to be a B. This is going to be moving up and down because both the high sides will hit and both the low sides will hit, and so it'll be going up and down twice as much as it would have been if only one of those waves had been. Okay, you guys remember what happens here? So I've changed to 10 and 10 and a half. Okay, some A's, a C, mostly A's. A is the right answer here, right? So you remember this picture. So this is 7.5 and 7 instead of 10.5 and a 10, right? But so if I count 1, 2, 3, 4, 5, 6, 7, actually this is 8 wavelengths, and this would be 1, 2, 3, 4, 5, 6, 7 and a half. This is actually 8 and 7.5. I counted wrong, right? And so at this point right here, this guy has traveled 8 wavelengths. This guy's traveled 7.5. And so he's traveled a little bit less far. So only halfway here. So this guy's only gotten halfway through his cycle. So he's up while this guy is down. And so these guys will always be completely out of phase. One guy will always be up when the other guy is down because he's traveled a little bit further or a little bit less far, right? And the rule here is how different the distance is between, right? The question is not how far did this guy travel and how far did this guy travel. The question is how much further did one guy travel than the other? If he traveled further, then he's delayed. And what we really care about is not even how much, we care about what fraction of a wavelength there is in difference between the two. Is it an even number of wavelengths or is it a fractional number of wavelengths difference? So for instance, what would I get if I had the two, and let's say I had, this was 9.25 wavelengths and the other one was 9 wavelengths. Or let's say 9.75 wavelengths. What would I have in that case? Would it be A, destructive, B, constructive, or C, between? So this is like nothing, lots, somewhere in between. Yeah, so this would be destructive. Just want to make sure everybody got this idea. So this is destructive. So this number doesn't really matter. It's really the difference between these two numbers. It's really L1 minus L2 divided by lambda. That's what we really want to know, is how many wavelengths different is it? If this is an integer, 0, 1, 2, 3, 4, then it's going to be constructive. If this is like a half integer, then this will be destructive. So that's the kind of number we're looking at, right? Now, instead of having the waves head straight at each other, what if I had them something like this? Some C's and some B's. Okay, pick someone. Nathan, why you think it's a B?
I said B because they are both integers. So that means, like, even though they're a different number of wavelengths apart, they're still in phase with each other.
Okay. Calvin, what do you have to say to that?
I would agree with that, I guess. That was
okay.
my
All right. Somebody else who answered B, do you disagree with that reasoning? No? Nobody wants to speak. I understand. Yeah, so B is the right answer, right? This is going to be an antinode. This is going to be moving up and down lots, because when this guy's high, this guy will be high. Now he'll be 5 wavelengths behind, but we don't care about that. We don't care that the first wave, it'll be 5 wavelengths ahead from one of them than the other. We don't care about that, right? So now what if I had 25 and 20.5? Right, so that'll be destructive, right? Because now it would be a half wavelength apart. So where I am, now obviously where I put point P will change the relative distance between this and this. So if I ever have the situation where I have 2 sources and a single point that I'm looking at, I'm going to see different amounts of waves depending on where I look. Now, for the case of light, how big the waves are corresponds to how bright the light is. If I have water waves, how big the waves are correspond to like how much energy is being put on that spot. If I have sound waves, the amplitude of the thing there is proportional to how loud the sound is. So there's lots of different ways that we can do this. So what I'm going to imagine here is we have a circumstance. And the easiest way of getting this, now having 2 sources of light that are both doing the same thing, or 2 sources of any waves that are both doing the same thing in phase, is kind of awkward to get to. But there's an easy way of doing it in real life, which is I have a single source that's sending out waves. So this is like a cork bobbing up and down in the water. And then some distance away from it, I put 2 holes. This is the slits that we're going to talk about. So these are vertical holes. And so when the waves come up to it, the waves are pretty much flattened out here. And so what hits this is like single flat waves hitting the top one and single flat waves hitting the bottom one. So then these guys will both have the waves spread out from them as though they're individual sources. So it's like this slit and this slit are like those 2 flashing sources. They're like 2 things that are creating waves that are coming out from them. So then what we have to do is we have to think about what will happen here. So let's say I've got some waves, right, coming from slit 1 and slit 2. And I can imagine that if I have, so something like this, right, these 2 waves, if I have them hit in the middle of the screen, right, they've obviously both gone the same distance. And so here I'll have constructive interference, right? if I move up, so this is going to be 2 slits, and this is going to be the piece of paper I'm looking at. And if I have constructive interference, it'll be bright. Or if it's sound, it'll be loud or whatever. If I look at some other position, so I bring it up here and look at some other position, then where it's hitting the screen, one is high where the other is low. And there I'll have destructive interference, and I won't see any light. It'll be dark. And then in some other position, it'll be constructive again, and then destructive again, right? So this sort of tells you, so where you're looking at it tells you the difference in how long each of these paths are. You can do this, this is kind of fun. I don't know if I don't remember showing this to you before. What I have here is I have 2 translucent sheets here. I'm going to turn this over so it's white. And they're just circular patterns. But I've got another one with another circular pattern. If I put them on top of each other, they're exactly the same. And as I pull one of them to the right, you get see this weirdness happening, right? So one thing you see is that here you see very, very defined light and dark regions. Very, very defined light and dark regions. But here, the light and dark regions are canceling out. It's just becoming a uniform gray. And so this is like no activity. This is like flat water. And this is like water with big waves. Now, as I pull them further apart, now you can see something slightly different. Now I've got gray here, 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 and here. And I've got black and white up, down, left, and right. As I pull them further apart, you can see now I've got 6 gray regions and more light and dark regions. As I pull them further apart, I get even more of this, right? So so you can see these diagonal lines running away. This is called a Moir pattern. It's really cool. You can make some very interesting shapes with this, right? And it's really most impressive when you move it left and right. You can see the lines move around, right? Which is just really cool. Now those lines are meaningful. The gray lines, those are the ones your eyes tend to focus on. At least my eyes tend to focus on the gray lines. Those are actually the lines where it's destructively interfering. And the other lines that are black and white, those are the ones where it's constructively interfering. So now you can just imagine putting it like this, and then by evolving over time, these bumps will all move up and down by themselves. So, or to give you the picture of it, let's share that Google thing again. So what I'll do here is let's turn this over to some medium light, and I'll make it into 2 slits, something like this. Let's make that light a little redder. So here you can see these 3 bands, right? There's the center band where it's the same distance from both slits, and you see a bright spot there, which corresponds to a big peak. And then you see there's this line here and this line here, which corresponds to 2 more spots. Now, if I turn up the, let me decrease the slit separation here, make that smaller. And let's turn up our, oops, my slit separation is 0. That's no good. I'll make that a little smaller. So as I bring up the wavelength, this is going to become more and more bumpy. Right, so you can see there's more than just 3 bumps. There's a bunch of bumps. So this actually happens in real life, and I'll show you an example of this in a second. But what we want to work out is where are those light and dark patches going to be if I have 2 slits? So for that, we can just do a little bit of math, a little bit of geometry. It's not even very complicated math. Right. So I've got 2 slits here. Call that slit 1. Call that slit 2. Right? And I've got a wave hitting it from the left, and it's making stuff off to the right. So what I really care about, so here's where I'm going to see the light on my screen. What I really care about is how far this one goes, this goes versus this goes. So I'll take a spot on my screen here, P, and I'll draw two lines. Let me see, I should use a straight edge of some kind here. So I'll draw two lines, one to there, one to there. So these two lines both hit this place, and what I care about is what's the difference in L1 versus L2. Now this is actually a really tiny diagram. These two things are very close together. Like these slits are very far apart for this screen being so close. In the real world, we'll have two slits very, very close together and the screen very far away. That's how we're going to actually do this experiment. So this is all a little condensed. If I think about this picture, right, and I think about this, well, one thing that's pretty, if you look at it, if you look at the angle that this is making from straight forward, that these rays are making from straight forward, an approximation you can make, which is pretty good, is that these angles are almost exactly the same. They're just a teeny, teeny bit different. So this angle and this angle in here are almost exactly the same. So the way I can think about this really is that, to redraw this diagram, is I have two rays coming off, and they're going in almost exactly the same direction. With some angle in here I'll call theta. But one of them will travel further before it hits the screen than the other. Now, if I want to know how much that is, this is the trick. I draw a perpendicular line like this. Now, this distance in here, that's the extra distance that the bottom ray had to go, right? They'll both go the same distance to reach that screen over here, or very, very similar, so close that we can't really tell the difference. But the extra distance is kind of this bit here, the bit where the bottom ray had to catch up to the front ray. And that is the extra distance that we care about. So I'm going to call that distance, I'll call that delta. That's the difference in distance between the two distances to the screen, between slit 1 and slit 2, right? Now I can work out what delta is by looking at this triangle. Now I know that this angle here is theta, and if I think about that, that actually tells me that this angle in here is theta, right? This and this are complementary, and then this, and so this plus this angle add up to 180 degrees, and then this angle and this angle also have to add up to, or have to add up to 90 degrees, sorry. So this angle in here and this one have to add up to 90 degrees, but also this one and this one have to add up to 90 degrees because it's a right angle triangle, because the sum of the three sides has to add up to 180 degrees. So, and we've done these like dozens of times in first year, right? Where we see there's a triangle and we have to figure out where the angle is. This is the same as the block on the slope problem. So that tells me for this triangle, which I'll draw one more time, I have angle theta in here, and I also know what this is. So this I'm going to call the distance between the slits. I'll call that D. So D is that length of this side, and delta, which is the difference between the two path lengths, is over here. Well, this is just trigonometry, right? This is the opposite side, and this is the hypotenuse. So delta over D is sine theta. Easy, easy. So delta is equal to D sine theta, and that's the difference in distances between the two have to go. Okay, so now let's say I want to have destructive interference, right? So what could delta be if I had destructive interference? Like what's one value I could have?
Like a half
A half what?
wavelength.
A half wavelength, right? Because this is units of distance, right? So a half of a wavelength, so this is the wavelength in meters. And if they're a half wavelength, then it's destructive. What's another value that also give me destructive interference? It could be a half off. What else?
1.5.
1.5. That's exactly right. 1.5 wavelengths. Or, right, this is the next one going to be easy to guess, right? It's going to be 2.5 wavelengths. So I have the condition that as long as delta is equal to m plus 1/2 lambda, where m is 0, 1, 2, 3, and actually it can be -1 as well, or -2 or -3. If it's a half an integer off, if it's any integer plus a half times the wavelength, then I'll have destructive interference. So that leads me to, so I get the dark spots at m plus 1/2 lambda equals d sine theta. So theta, so d is the separation between the slits, lambda is the wavelength of the light we're using, and theta is where I'm looking at it on the screen. So this is my two slits are over here at some place, and then theta is the angle I'm looking at over here. Now, for this, one way I could do that is probably what I want to do is I want to measure where is that point, where is that dark spot relative to, say, the center of the screen, directly across from the two slits. So if I wanted to do that, this L then could be the distance between the slits and the screen, and X could be how far it is. And in this case, to a good approximation, sine theta is approximately X over L, because the distance to the screen, as long as this X is small, sine theta is about the same as tan theta. That's an approximation we can make, and so we made a couple little approximations, but these angles tend to be quite small. We're looking at like only a couple of degrees here. So these approximations are really quite good. So if we put that all together, what we get is we see dark spots, that is to say destructive interference at m plus 1/2 lambda equals d X over L, or d sine theta, if we want to be a little bit more accurate. So, or to put another way, the place I'm going to see the long spots is going to be L over d times lambda m plus 1/2. So these are the places where we see dark spots. What equation would I use? And I'll often just write it as, I'll just write it as this one. I'll just write it as m plus 1/2 lambda equals d sine theta. That's usually the one I do. And then this X over L is usually something you do when you're doing the measurement. How would I change this formula for the bright spots? How would I rewrite that?
Take away the 1/2.
Take away the 1/2, exactly. So that's going to be the bright spots, right? So this is again for m equals 0, 1, plus or minus 1, plus or minus 2, plus or minus 3, etc. This is called the order of the spot. And so clearly one place you get constructive interference is at m equals 0, which means this side is 0, which means theta is 0, which means that X over L would be equal to 0, and that's the middle, right? So that means that right in the center, you're going to see a bright spot. But you'll also see a bright spot in other places where you see this, and you'll see dark spots in between. So this formula tells you what angles you're going to see the dark spots, and this formula tells you what angles you're going to see the bright spots. Share screen, do thingy. So here's that whole picture again. So what it actually looks like is something like this, is this middle picture you can see here. You have light coming in from the left, it goes through two slits, and it makes this pattern of light and dark. Now the pattern you're looking for is these little tiny black streaks. That's really the interference pattern. There's also, it sort of fades in and out, and that's because of the size of the slits themselves. That's the single slit thing happening. So really, I want you to pay attention to the fine detail of the black pattern, of those little black horizontal lines. And those are places where the light is destructively interfering. and not constructively interfering. And if you plot that out as an intensity plot, you get the thing that looks like on the right. It's like the middle ones are much brighter and it gets dimmer as you go off to the side. But basically you can see this pattern. Now you can do this yourself at home. And how I did this is I took a washer. So this is just a, I'll show you this in a minute. Let me show you that. I don't want to switch cameras again. Let's go back to this guy. So you'll see it more strongly. The pattern will be bigger with redder light because that means that lambda has gotten bigger. And so that means theta has gotten bigger. And so that means you see it at a broader distance. So the pattern is large. So with a big wavelength, like red, you see a big pattern. And then at small wavelengths, like blue, you'll see a narrower pattern. The peaks will be closer together, right? And if it's very high wavelength, the peaks will blur together and you won't be able to see the differences. So if you have, and it depends on the size of your slits, but basically it's harder to see with green light or blue light than it is with red light. That's one of the reasons we put a red laser in your package. The other reason we put a red laser in your package is because the red lasers are cheaper. But it was both are, so that's a happy coincidence. So what I've done here is stop sharing. So what I've done here is I've taken a washer I just had lying around, and I got a couple of pieces of masking tape, and I put the pieces of masking tape over it so that I made a narrow slit, about a millimeter or a half millimeter wide. I just lined up the pieces of tape and taped them down so that I had a hole in between them. And then, I don't know if you'll be able to see this. Let me focus on it. It's actually very hard to see for the very reason that we've got, let me see here, I put it here, focus on it. What I did is I took apart the gray wire, like a short piece of the gray wire. No, I can't see it. I took a short piece of the gray wire that was in your kit, and I took the insulation off, and I took off one of the strands of wire. So the gray wire consists of a bunch of strands of silverish wire that are twisted together. I just untwisted one of those strands, and you probably can't see it, but I put it along the center line in this slit. And you can do that if you tape it carefully and you put it in the middle. So now what you have is two slits. You have the slit on top of the wire and the slit on the bottom of the wire, and they're very close together. Now, if you take red light and shine it through, the first thing you see, so let's get rid of that stuff. So the first thing you see, so I'll just take my laser like this and I'll shine it through. The first thing you see is that the laser spreads out along the length of the short side, right? And that's because the waves are just diverging out from around this short entrance. The entrance is small, and so that's making them spread out. And now what I'll do is I'll stand up so maybe we can see the interference pattern. I gotta get my wire centered there. Wire lets move around. So I'll hold it up really high. Now, I don't know if you can see it. Now, it's not coming through very clearly on the screen. Let me see if I get my focus back. Maybe what I'll do is this. I'll put it up really close. Focus it. Okay. And now I'll take my guy. The wires keep shifting out of alignment. You can just barely make it out, the light and dark streaks there. Again, this is the kind of thing that's much easier if you throw it on the wall across, so if you project it across the room. But this is the sort of thing you can try yourself, and you can justify yourself this really works. A really poor man's version of this is take your fingers and put them so your fingertips are just barely not touching. And then look through the gap at something bright. And what you'll actually see if you look through the gap is you'll kind of see, this will be your top finger, this will be your bottom finger, and you'll kind of see kind of a lines between them. It's a small little optical illusion that you can get. It kind of, your fingers blur together a tiny bit when you do this. And basically you're seeing the same effect. You're seeing this narrow slit effect creating these little interference patterns. So there's a bunch of ways you can see this in real life, but people didn't really notice this for hundreds of years. People didn't really notice that this effect was happening. They just, They just thought this was their bad eyes, or they shut it out. Basically, we're not in the habit of making tiny little holes in things and looking at the result. Now, there's other ways of doing this as well. Let me stop here, though, and let me ask you a tricky question. Oh, this experiment, I should say, this is called Young's experiment. The two-slit experiment is called Young's experiment. Young did this in the 1890s or something. Let me just explain what this is saying. We're gonna have two slits. I'll make them really big just to illustrate, just as before. So we're going to shine the light through the two slits, and so there's a distance between the two slits, just as before. But now I'm going to put a polarizer like this on front of one slit, and a polarizer like this in front of the other slit. And so now the question is, do I still see the interference pattern or not? That's the question. Most people answering D, it looks like. Yeah. Aaron's thinking about B. So you're thinking that this will shift it Y, that it'll shift the fringes how?
I'm trying to imagine if it's either going to be like just shifted, I don't know, by wavelength, or I was also convincing myself that it could just always be out of phase and have nothing.
Yeah. So what the difference is here is by putting the polarizer on, we're actually not changing the phase of the light. We're just changing which way it's oriented. So the two beams will still be in phase, but one of them will be going up and down like this, and the other one will be going back and forth like this. But now what you notice is that now they don't interfere with each other. If I have something, if I wiggle a string up and down, and you stand on the other side and wiggle the string side to side, these two things they won't interfere with each other. The up and down motion won't interfere with the side to side motion. It'll add up, so it might make it go around in circles, or make it go back along a diagonal or something like that. But they don't really add. They add like vectors. They don't add as numbers. So the right answer here is actually what most people are guessing, which is that the two will just act as though they're two slits without interference, as though they don't have any relationship to each other, and the interference pattern will disappear. Which, because you've changed what you're adding up. You're no longer adding up this and this, and this and this. Now you're adding up this and this, and those two don't add the same way. So there you destroy the interference pattern, and you get a regular spot. This is a very subtle question, and so don't worry about it if that one's puzzling to you. But it shows that there's a lot of rich variety happening here. Now, for the purposes of what you're going to do in lab next week, we're not going to use two slits, because the two slits is just hard to do. And also finding a really nice two slit is difficult. So what we're going to do is we're going to do something else. We're going to add some slits. So instead of having two slits, maybe I'll have 1, 2, 3 slits, and I'm going to have them all the same distance apart as they were before. So the slit spacing for the first two and for the second two are the same. So I'm just add another slit, or maybe I'll add a third slit or a fourth slit. So now we can think about what's going to happen when we do this. Well, we can draw the same picture as we did before. So I'm going to put the screen far off on the right here, and I'll have a line coming from the first one going somewhere, and from the second one going somewhere, and the third one going somewhere, and eventually these will all converge to the same spot on the screen. And again, the screen's far away, so we'll make the same approximation, and so these are all coming off at that same angle, or very close to it as it was before. And now we can think about how much further the second one goes, where we could draw our little right angle triangle again. And then we could draw another right angle triangle here and here. So this is how much further the second ray goes, and this is how much further the third ray goes, right? So if you think about it, let's say, so this is delta. So this, let me draw again. So I've got boop, 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 boop. Drop down the diagonal like this. This in here will be delta, and this here will be 2 delta, right? This is going to be twice as far, because it's basically just the same triangle, but bigger. It's twice as long on this side, so it'll be twice as long on this side. So that means that if I have more slits, they're all going to follow the same constructive pattern. So I'm still going to have m lambda is equal to d sine theta will still be constructive, because these guys are going to, these guys will all be the right length still, so they'll all create a constructive spot. You'll also find that if I have m plus 1/2 lambda, this is still destructive. So because this guy and this guy will be 180 degrees out of phase, and let's say I have 4 slits. So this guy and this guy will be 180 degrees out of phase, and this guy and this guy will be out of phase. And so these two will cancel each other, and these two will cancel each other. Actually, if I have 3 of them, then one of them won't cancel, and then I'd still see some light. But if I have a whole bunch, like an even number of slits, then these two will cancel, and these two will cancel, and so again, I'll see a dark spot. So these rules still hold. Let's show you a picture of that. So this is constructive interference, right? Here, the difference in path length between this ray and this ray is lambda, and between this ray and this ray is 2 lambda, and between this ray and this ray is 3 lambda, and between this ray and this is 4 and 5 and 6. So these are still all in phase coming out of here, and we'll see constructive interference. This is where I have it, where I have half a wavelength here and a wavelength here. So this guy and this guy are half wavelength apart and they cancel. This guy and this guy are half wavelength apart and they cancel. This guy and this guy, this guy and this guy, every pair of them is a half wavelength apart, so they're canceling their neighbors. But then here's the interesting condition that you get. So far, what do you think is going to happen if I have many slits instead of just 2? What's going to be the difference between those 2 patterns? Will there be any difference between a 2-slit pattern and like a 6-slit pattern?
Is there going to be more like areas of light and then like dark areas? Like there's just going to be more of them, like closer together, I guess.
So there won't be more of them. No, they won't be closer together because we just said that the angles will all be the same. But there is more because there's more slits, right? So there's more total light making it through the barrier, right? There's 3 times more light makes it through the barrier. So everything's going to get brighter. That's the first thing, is it won't be such a dim pattern anymore because we're just letting more light through. So that's the first thing. But then here's the second thing that's cool. Let's look at a number that isn't exactly right. So let's say I have the first distance is going to be 3/4 of a wavelength. Now, normally, this would mean that the first 2 rays are 3/4 of a wavelength different. So they're not exactly out of phase and they're not exactly in phase. So this would be a gray spot. This would be where it's not bright and not dark. It's somewhere in between. But now if I have this guy, he's 1.5 wavelengths apart. But if I look at him, this one and this one are now destructively interfering. And this one and this one are destructively interfering. This one and this one are destructively interfering. This one and this one are destructively interfering. So now, if I had only 2 slits, I'd see a gray spot. But now if I add more slits, there's more ways you can get destructive interference, and it can kill each other. And it turns out the way this works is it always does more destructive interference than it would have before. So if you look at nearly any angle, if you have lots of slits, you're always going to find another slit that'll destructively interfere with the first slit. So you can always find pairs of them. So if I have a thing that's made up of many, 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 many slits, like hundreds of slits, then I'm going to find a lot of cancellation. And what this is this is called the diffraction grating. It's a grating because it's like a grater. It's got these holes in it, these lines on it. And this is what you were given in your kit, because it turns out you can make these now very cheaply. It's this guy that was put into your that you were put into your kit. This is a diffraction grating, and what there is there's 500 lines per millimeter. So that means every millimeter has got 500 holes in it. And if you just look at it, it just looks transparent because there's just lots of light can come through. It's like half whole. It's a little bit dimmer than a regular thing. And this is very thin lines every 500 millimeters. You probably could see it if you put it under a microscope. You could probably see these individual lines. But the net effect of this is that not only is the light that gets through brighter, it makes the spots very narrow. So there's only a very narrow place where you get constructive interference, and most of the rest of it is destructive. So if I take my red laser and my diffraction grating and I shine it through, I get this. I get spots, right? I get individual spots. So those are each places where I have constructive interference, and I get big dark spots in between where there is no light, and that's all destructive. So you get places with very, very strong constructive interference and places with not much constructive interference. Hey, you can use this. And if you know what this is, this tells you what this is. Now we still have this rule, except with the diffraction grating, instead of knowing the distance between, I know how many lines per millimeter I have. So in this case, it's 500 lines per millimeter. So that means it's 1 millimeter per 500 lines. So this means that the distance between the lines is 1/500th of a millimeter. So 1 millimeter divided by 500 is the distance between lines. And so I could use that to find that out. That's basically the whole thing. That's what we'll do in lab. This is one of the little tiny experiments we're doing in lab this week. Now, of course, if you have access to a green laser pointer, this is kind of neat. So what I'm going to do is I'll take both the green laser pointer and the red laser pointer, and I'll shine them both through at the same time. And I can't shine them in the same place exactly. Oh, maybe I can do it in the same place if I do it like this. Now, one thing you'll notice is the spots don't go in the same place. If you look at the green spots on the bottom, they're closer spaced than the red spots on the top, right? So this tells us the wavelength. We know that the distance in the spacing, which gives us by sine theta, or the same thing as x over distance to the screen, is equal to 1 over lambda over, m lambda equals d sine theta. So if lambda gets bigger, the theta gets bigger. So as I move up in color, I move from red to green to blue, this gets smaller, so the theta gets smaller, so it gets narrower. And in fact, this is the method we use for measuring the wavelength of light. What you do is you put it through a diffraction grating, you see where the light comes out, and that tells you the exact wavelength. We use this for all sorts of things. Spectrophotometers use this. If you're going to measure the colors coming out of an object or the colors going through the object, you want to measure stuff. We use this in astronomy when you want to know what the colors are coming from a star. This is how we know the sun is made of hydrogen. It's because the different colors coming in are the colors of hydrogen. So you can do this stuff. So this is a pretty useful device. And you can use this for all sorts of measurements, and it's kind of cool that you can have these. Now, one thing you can get is if you take this guy and you look out the window at it, what you'll see a rainbow, because what's happening is the different colors are coming out at different angles. So it separates off what you're seeing into a rainbow color. You'll notice this often doesn't work with indoor light. If you use this in front of your computer monitor, it's not going to work because your computer monitor doesn't actually give off white light. It actually gives off some red light, some blue light, and some green light. And that tricks your eye into thinking it's white light, but it's not really white light. So you want to actually see this. You might, if you do it carefully, you can see 3 bands of light if you look through it this way. But if you look at it through the window or at an incandescent light bulb, you'll see a rainbow effect. And that's the light spreading out. So it acts like a prism.
So how does an actual rainbow work?
Say again?
How does an actual rainbow work?
Oh, so an actual rainbow, we'll talk about that later. That comes from dispersion. I hope we'll have time to talk about it. And the reason is that the light refracts differently. And we're going to get to that on Monday, or Monday or Wednesday. We'll get to the mechanism going on there. So it's a little different. Now, another thing that you could guess, looking at this, if you think about it for a little while, is that you could get this same effect not just from light going through a whole bunch of little slits, and then projecting onto a screen. Another way you could get it is if you had light shining on a bunch of tiny little mirrors and then coming off, because each one of these mirrors would act the same way as a slit, and so would also provide interference as you did that. And there's actually a place where, well, it's becoming less common now, but there's a place where you see this all the time, where you have lots of tiny little mirrors in a row, and that's CD. CD consists of lots of tiny little tracks with reflective and non-reflective surfaces that just in between the tracks. And if you ever look at one of these things, there's always a rainbow on it, right? You can always find a rainbow along one of the directions. Let me see. There, you can always find a rainbow on a CD, but when you're looking at it, and that rainbow effect comes from the same place as the diffraction pattern. It's acting as a reflective diffraction gradient. So this is another place where you start seeing these sorts of effects. Another place where you see this is, let's say I have, instead of, I'm going to take reflections again, and I'm going to take reflections off some tiny little things. So I'm going to shine some light on it of some wavelength, where the wavelength is about the same as the distance between these tiny little things. Well, each one of these guys will re-radiate, and so again, I'll get constructive interference in some directions and destructive interference in other directions. Well, if these tiny little things are atoms, then the right wavelength to use for this is X-rays. And so if you take a sample of something that's made of a regular spacing of atoms and you shine X-rays on it, you can move an X-ray detector around, well, here, and you can measure how much X-ray bounces off the thing in different angles. And this is an X-ray diffractometer. This is what Dean Johnson has up in the lab on the 3rd floor, is an X-ray diffractometer, which you can use to measure the interatomic spacings of a crystal. And sometimes there's more than one interatomic spacing for complicated crystals. And so we can use that information to pull out how the arrangement of atoms is in that crystal, which is very cool. There's also another version of it using a powder where they're all mixed up. But the basic ideas are the same, is it's looking at constructive and destructive interference of waves, electromagnetic waves, bouncing off of lots of little things arranged in rows. So this is not a minor thing in our world. This is actually a really important technique and important device for doing this stuff. So there's a couple of questions on the homework about this, and there will almost certainly be a question on this in the homework on the final exam. Let me see, do I have a copy of the one I had used previously? I don't know if I can find it here. But it's not uncommon that, for instance, I'd have something like what's in the homework where you're given a picture and you're asked to figure out what wavelength of light there is. Or I might give you the picture that looks like this. And then the distance between these peaks tells you how far apart and it tells you about the wavelength, or tells you about the distance between the slits. So expect a question like that. This is definitely going to be on the exam, because this is really one of the most important things in physics. The bit we don't have time to talk about, and really takes a whole course, is that this happens for other objects too, like electrons and protons. And in fact, any object acts like this. It turns out that all objects are low wave-like if you look at them the right way, which is completely head-bending. We do not have time to talk about that, but there's excellent lectures online. Feynman lectures are really good on this. the Feynman Public Series has a really good lecture on this. So this is not a little thing, right? This is a big part of how we know the universe works. Let me see, was I going to say something else here on this topic? Oh, there's the question I put on the. So there's the kind of question I once put on. This is the 2016 exam. So which one of these is from a diffraction grating? Which one of these is from a double slit? Which one of these is from a single slit? Right. This is double slit. This is the diffraction grating. This is the single slit. And then, if you're given numbers, can you figure out the distance between the widths of the double slit? That was a question I gave in 16. So be wary of that. But basically, we don't see these effects very often because in order to see them, you have to have very long wavelengths. Longer wavelengths have got bigger effects. The only way we're seeing this is if we look at at distances the slits are very close together, much less than a millimeter. And it's just not very often that we look at things on that scale. On a larger scale, light basically doesn't bend very much. If I have a shadow, or if I shine light on something I have, and like this, basically what I'll see at the bottom is I'll see a shadow, I'll see the bright here, and then I'll see dark on those sides. We don't see much of this spreading because the spreading is actually very small. It's appropriate to the wavelength of the thing. If we have a short wavelength, this spread is proportional to the size of the wavelength. And for light, that wavelength is nanometers, hundreds of nanometers, and so we don't see this. It does show up in several different ways. Shadows are fuzzy, even under optimal conditions where there's no air, there's no scattering in the air, and you have a very sharp surface, you still get fuzzy edges to your shadows, and that's the diffraction taking place. Another reason we don't see this is because the light is not monochromatic. It doesn't have a single wavelength. It's got lots of wavelengths. So all the wavelengths will have different effects and smear differently. And we kind of then don't notice it quite so much because the red and the orange will spread differently, and so that kind of washes itself out. And our eyes aren't very good at picking out those sorts of things. So there's lots of reasons we don't notice this in day-to-day life, but it's definitely there, and it's definitely a part of how light works. Let me see, is there anything else I want to talk about? Well, let's do a quick. There's an easy one. So it's spreading out horizontally. If it spreads out horizontally, that means the horizontal width of the slit had to be the narrow one. Big slits, this doesn't happen. Big holes, it doesn't happen. Tiny holes is where you see it. So the tiniest must be in the horizontal end, which means the slit must be vertical. So it must be a slit that's aligned vertically. And you'll see that when you're playing with either your double slit, if you make a little double slit or you make one of these guys, you'll see, yeah, which way is the diffraction pattern? It's always transverse to the direction of the slits. Anything else I want to briefly go over here? I think that's pretty much it. There's a lot of other interesting stuff that comes out of this. Like for instance, there's a limit. There's a fundamental limit to how close together two objects can be, and we can still see the difference between them, which is important in astronomy. It's important when you're looking at the horizon. There's a limit to how good, even if you have a perfect telescope, there's the fundamental limit to how fine detail you can see two objects. And it's got to do with the aperture that's on the thing. So there's a lot of effects, these physical effects, and we can go into a lot more detail on diffraction. Two-slit diffraction is really the most understandable. Two-slit interference is really the most understandable, and so that's what we're going to focus. So that's the only thing we're focusing on this time. Okay, so on Monday, I'm going to start on geometric optics, which is to say, let's ignore all this fuzziness and let's just talk about it as if light traveled in straight lines. What does it do then? And so we'll talk about reflection and refraction, total internal reflection, And so we'll have about part of that ready for the lab on Tuesday, and we'll finish up talking about it on Wednesday. And then that's going to be the course. We're leaving out tons and tons of useful stuff. We're not going to have time to talk about lenses. We're not going to have time to talk about rainbows very much. I could probably answer that on next Friday. But we can, enough so that you can get the idea of what's going on with light before we end the course. And this is just one of these places where I'm sorry you're getting gypped on content. We can't do all the fun stuff at this point just because we don't have enough time. Okay, so get your homework in if you haven't already. Get it in by the end of the day. Next homework will be due hopefully morning, a week from today. And that day will be review day. And then a week after that, we'll have our final exam. And then we're done. Home stretch. Keep moving. Have a good day.